Okay, so now that we've learned how to make an almost perfect adder, the circuit to perform the summation of two given integers, let's learn how to compute the next arithmetic operation, the subtraction. So assume that we have two integers given by their binary representations, and assume for convenience for now that the first integer is greater or equal than the other. So now let's consider their difference, x minus y. Well, actually, instead of considering this difference, we'll consider the number 2 to the power of n plus x minus y. And actually, if we look at binary representation of this number, then its significant bits that actually interest us, the rightmost n bits, are the same for both of these numbers. Because if we subtract two such numbers from one another, we get a number which fits into n bits. And 2 to the power of n just adds basically 1 here. So if we forget about this bit, if we're able to compute the difference of the two numbers, then we're able to compute this number as well for free, almost for free, and vice versa. So if we are able to compute this number, we'll just forget about the leftmost bit, and we see that the rest of the bits actually represent x minus y. So we'll see how to process and compute this thing. And this thing we can rewrite as x plus 1 plus 2 to the power of n, which comes from here, minus y plus 1. So we see that both ones, they also vanish, and we get just the original quantity. But now, what ingredients do we need to compute this expression? It doesn't look simpler than the original one. But if we now rewrite this part of the expression as 2 to the power of n minus 1 minus y, this one can be actually computed almost for free. Because 2 to the power of n minus 1, 2 to the power of n minus 1, the binary representation of this number is just a bunch of ones, n consecutive ones in binary. And the difference between this number and number y, which is represented by its bits, the difference between these two numbers is just the negation of all these bits. So we can immediately compute the difference between such two numbers, because the first of them is really magical. We do not have to think about carry bits and so on, which we usually have to think about when subtracting. So no borrows here. Everything is done by a single layer of negations, of Boolean negations. And the final thing that we need to have here is two additions. So one addition here and one addition here. So let's see how we can build the circuit. So we take y0 through yn minus 1. We supply all these bits to the layer of negations here. Now we take x0 through xn minus 1. And we also need constants 0 and 1. So we can take, say, yn minus 1 and negation of yn minus 1 and compute a conjunction of them, which will give us constant 0, and also compute disjunction of them, which will give us constant 1. So now here we have both constants, 0 and 1. And now we can pass all these inputs for x, and we can pass 1 here and many zeros elsewhere as a binary representation of this number 1. So we already have a circuit which is able to add numbers. We add 1 in its binary n-bit representation with x in its n-bit representation. And thus, on the output of this subcircuit, we have x plus 1. Now, finally, this layer of negations produced us this number, and we need to have yet another adder, which gives the output of the previous adder and all these negations. And finally, the adder will provide us with z0 through zn, where zn will actually know what this bit would be equal to. So this bit would be equal to 1 because this number is at least 2 to the power of n. And we just can get rid of this bit. So we do not treat this as a real output of the circuit. We use only outputs up to zn minus 1. So this would be the result of our computation. So now the question that we still need to answer is what if x and y are not in this relation? So what if x is less than y, or what if x is equal to y? A decent circuit for subtraction of two numbers should actually deal with that on its own. We do not assume anything about the relation between x and y. So, okay, at least we can use this guy as soon as x is greater or equal to y, and then we need to be able to compare two numbers. So how do we compare the numbers? Well, we look through the most significant bit to the least significant bit in this direction, and as soon as we have difference here, so for instance, if xn minus 1 is greater than y minus 1, then we immediately know the result. Independent of all the other bits, we know that x is greater than y. If these guys are equal, then we look at the next pair of bits, and if we have any kind of relation like this, we know that this relation actually determines the relation between the numbers themselves, and so on. So essentially, we just skip the bits while they are equal, and the first pair of unequal bits allows us to compare the two numbers. So actually, the situation is very, very similar to the computation of carry bits using parallel prefix circuit. Because here we have three types of relations. We have equality relations, greater or less. And we can now use these as values. So let's take the results of these comparisons. For instance, left to right, we compare two numbers, and for their pair of bits, we get these relations. So what would be the result of comparison? So we see that up to some moments, we have equal bits. Then we have the first number outperform the second one. So the first number is greater than the second one. And so we can build a table for this operation, which gives us like the result of previous comparisons and the current comparison, and tells us what is the result of these like next step. So if we had equality before, and if we have now also equal pair of bits, then so far we have equality between the two numbers. If our pair of bits is like this, then the first number is greater than the second. Otherwise, the first number is less than the second. Now, if so far we already know, like say up to this moment, that the first number is greater than the second, then this bit actually does not change anything in this relation. So here we would have this result. And if the result so far was like this, then we have this kind of result. So we see that this table actually looks a lot like the table for carry bit computation. And we can compute the result of comparison between two numbers as well using the parallel prefix scheme. So here we do not need actually these intermediate comparisons, we just need the results of this whole product of all these individual bit comparisons. Okay, anyway, this can be done in logarithmic depth. Actually, we now know that's the total size of the circuit, even if we employ some extra computation to compare the numbers and then to produce a signed output, the resulting circuit would be of size at most big O of n log n due to us using adders, and the depth would be as well logarithmic as the adder depth. So the resulting circuit, which would be, I think, a proper one for the computing the difference of two numbers, of two integers, would be the following. So we have the circuit which provides us with subtraction of numbers like this, and we prepend it with a circuit which computes the relation between x and y, so which one is greater, compares x and y, yn minus 1 through y0. So first we have a circuit to compare x and y. It produces one of the two results. Either they're equal, or x is greater than y, or y is greater than x. We can encode this using two Boolean values again. So we can say that if we have 1, 0 on the output, then this circuit means that x is greater than y. If we have 0, 1, then this circuit tells us that y is greater than x. If we have two zeros, then the numbers are equal. So in case when we have two zeros, we need to output 0. In case when we have this relation between the numbers, we see that we just need to subtract y from x and take the result. And if we have this relation between the two numbers, we need to flip them in a flipped way. We need to subtract the smaller number from the greater, but then add a sign to the result. So we'll need an additional bunch of small building blocks that take input bits x, y, and the result of this comparison. And such building block, it produces two outputs. So these outputs actually store the same inputs, like y0 and x0, but sometimes they flip the inputs, so that the rightmost output here is the output of the smaller number, and the leftmost output is the output of the bit of the larger number. And then we wire these guys here and here, and we have this kind of flipper for each of the pair of input bits. And every such flipping circuit, like swapping circuit, also takes these two outputs. So we have this layer of swapping circuits, and thus we are able to produce the result for any pair of input numbers, independent of their comparison.